Hello, welcome everyone. In this short video, we will look at the Osi Reference Model and the tcpip protocol. Before I begin this video, I would like to make sure everyone knows that this video is 10,000 foot view into OSI and tcpip. This is not intended for network professionals. This is primarily introduction for people who are trying to get into the IT industry or for that matter QA industry, and this video would give you a basic introduction and you will know a lot of terminology and a lot of basic things. So when you talk to people in the industry, or when you get a job, when you work with colleagues, or when you work with your network team, you'll be able to talk efficiently using the knowledge that you gain in this short video. Okay, let's dive in. First, let us look at the objectives of this video. We'll look at OSI reference model. Then we'll look at the TCP/IP protocol stack. Then we'll also talk about what TCP and UDP are, and then we'll touch base on the ports as well. Okay, then that would be our objectives for this video. So before we jump into the actual, topic of the video, let me start with an analogy. Say, for example, you have two people, John and Peter. Now, if John and Peter wants to communicate, what do we need? I mean, we are human beings. We all know that we need to know some sort of language to communicate. To be more specific, it has to be a common language, meaning if John only knows English and if Peter only knows Spanish, then there's a problem. They don't have a common language. Now in this real-time situation, you might need somebody who knows both the languages, can act as a translator. But primarily we'll focus on two people trying to communicate, and as we know, we need a language. So that's where we would start. So people needs to have some common language. They need to know the grammar, which are the rules, so that they can use the language. And of course, little manners. Is that really needed? I guess professionally, yes. So primarily, for two people to communicate, we are saying that we need some language, people need to know grammar, and use it for communication. In simple words, this is exactly how computers communicate. So let's look into the details now. Okay, OSI stands for Open Systems Interconnect, and OSI model is a reference model, meaning it's a open paper that was published saying or explaining the details on how computers can communicate, and that's why they call it as a reference model. So in OSI, we have 7 layers. So these are the 7 layers. The numbering always starts from the bottom. When they say layer 1, it's always physical layer. So 1, 2, 3, 4, 5, 6, and 7. Application layer, presentation layer, session layer, transport, network, data link, physical. So let me put alphabets here: A, P, It is very essential for you to remember / memorize these names in the order, because that's how the data communication occurs. You cannot replace or swap these layers. That's not how it works. So you have to remember this way. So now there is a specific role for each layer, meaning there is, again, as I said before, it's a reference model. That means it's something that happens. You really don't see all this. So what it means is, logically, when something is trying to communicate, or in other words, when system A is trying to communicate with system B, then number one, something in that system A is trying to communicate with something in system B. That something is nothing but application. Now when this communication happens, and how does the data presented, how the session is handled? Session means the actual communication between A and B, the two computers. Now how is the connection handled? Now how does computer A, or the first computer, how does it know the computer B? Or what kind of network cable that is used to connect both the computers? So all that is handled by different layers, and that's why logically they have this order. This physical represents practically the actual network cable, and application represents the actual application that is trying to communicate. For example, let's say you're trying to use your browser to go to your hotmail.com. So your actual browser action is at this layer, and when your actual data gets onto the network cable, that's at this layer. So that is Osi Reference Model. I'll provide a link on the eLibrary website where you can dive into and study more about each layer if you're more interested, and then you can look at it and definitely contact me with more questions. Now let's take a look at how these computers communicate in a little detail. So we have two computers, PC1 and PC2, and as we discussed before, we have these 7 layers. So let's say the whole idea here is PC1 is trying to communicate with PC2, meaning let's say you're trying to transfer a file from here to here. So in order for the file to reach from the source to the destination PC, it has to go through these layers. That's the whole idea here. So I'll talk about these arrows, what it means when I connect application on PC1 with application on PC2, presentation layer on PC1 with presentation layer on PC2. We'll get into this later, and so forth with other layers. Okay, this is the picture. So let's say again file PC1 is trying to transfer a file to PC2. Let's say that file is big and your computer breaks that into small pieces, and now let us assume that this is the first piece of the file that is being transmitted, this one. Okay, that's a data. Now when the application passes the data to the next layer, this presentation layer handles the presentation. It adds its own header to the data that came from the top layer. So the presentation layer adds this and passes it to the next layer, which is a session. So how the session needs to be handled, it adds again little header. Now the session layer passes it to the transport layer. This transport layer, practically whatever comes from the top is treated as data at that layer. So for the transport layer, this whole thing is the data. It takes the whole thing. The transport layer again adds a header similar to the layers above, and then it's passed to the layer below, which is network. Same thing, a header is added, and then the whole thing is passed to the data link layer. And the data link layer does the same thing, adds a header, passes it to the physical layer. Now the physical layer, what it does, it adds a header and a trailer, and then this is put on the, now it's added to the wire, the actual physical cable. Now it's passed on to the cable. Now this packet now travels in the network cable, reaches the destination PC. When it goes here, the physical layer, what it does is it strips off the header and the trailer, meaning it will remove that, read it, and pass the remaining portion, which is here, the white portion, to the layer above. So whatever the physical layer added on PC1 is read by the physical layer on PC2. Now when it is sent above, which is the data link layer will strip off the header added by the physical data link layer on the PC1, and then remaining portion is sent to the network layer. Same thing happens, and finally the packet is received by whatever is in the application layer. And we will take an example and talk about it. So the whole point here is when the packet or the data is sent from PC1 to PC2, the packet gets built with all these headers and then trailer on the source machine, and as the packet goes up on the destination PC, the headers, whatever was added, is read and removed, and the final data reaches the very top layer, which is the application layer. An example for this is, let's say for example you're trying to transfer files using a protocol called FTP, file transfer protocol. It's an application layer protocol. So when you use it, the FTP actually sits in the application layer as I said. So the FTP program or process on PC1 here communicates with FTP program here on the PC2 side. So the data is actually sent from FTP here to FTP here, but it has to go through all these layers. Again, to repeat, so when you transfer something, it is sent through all layers, and every layer adds a header on the source machine, and when it goes to the destination, the layer is removed, or I mean to say the header and the trailers are removed, and the data is passed up the layers. So that is how the whole data is transferred from one device to the other device. Again, this is a reference model. There is no such thing called OSI protocol, right? It's just a reference. It's almost like a blueprint on saying, hey, this is how the communication should occur or happen. This is almost like having a blueprint of a car. You're saying, hey, this is how a car should be. A car should have 4 wheels. A car should have a certain shape. A car should have a steering. 4 people as a capacity, or 5 people. You're saying that is how a car should be. But when that is taken by, say for example Toyota or Honda, they take the specs of car and they build, but both build in a different shape, right? Their own model, but they have the same reference as a car. In this case, OSI is a reference model as such, but it is not a protocol. It's a reference model. But the tcpip, which is the actual protocol, was built based on this Reference Model. So I hope you all kind of understood the OSI layers. If you prefer, pause, go back, rewind, and watch this last 5 minutes again. Now let's get into TCP/IP protocol. Now in TCP/IP, all you have is 4 layers. Application, transport, internet, and physical. The functionality of 7 layers is now converged into these 4 layers, meaning one of these layers kind of picks up the functionality of multi-layers from OSI model, meaning the whole functionality of the 7 layers is handled by the 4 layers in TCP/IP. Now, at application layer, the example I listed here is telnet, FTP, and DNS. That's just example of application layer protocols. Even your HTTP is also application layer protocol. When we talk about web servers, we'll refer back to the TCP/IP model. Protocol layer stack, to kind of refresh again what exactly this HTTP is, TCP/IP, and FTP is. You really need to use it to understand it. And when we talk about web servers, we will revisit this topic. In the transport layer, you have TCP protocol and UDP protocol, and what they are is that's a protocol that is used to transport data. TCP/IP is a connection oriented, meaning both the parties actually connect before transmitting data. When it comes to UDP protocol, it's connectionless, and what it really means is there's no connection established to send the data. So an example is, say for example, let's say John is trying to communicate with Peter using his cell phone. So he rings the phone, Peter picks up and says hello, and then John starts talking, meaning Peter has to pick up the phone and answer for the whole communication to occur. If this person Peter does not answer the phone, then obviously both people cannot communicate. That means there's a handshake going on. That is how the TCP/IP works. UDP is like a flyer, meaning let's say for example a Target is sending a weekly ad. Through mail. They don't care whether you're living at that address or not, or who lives at that address for that matter. It is just sent to that address and it goes there, and whoever lives there receives it. And Target really, they don't care whether you received it or not. And that's how UDP protocol works. TCP/IP, it's connection oriented. Example is 2 people trying to communicate using cell phone. UDP is connectionless. Example, a company sending out flyers. And next is internet layer. This is where internet protocol, which is IP addresses, come into picture. For communication, we'll look into IP addresses in another video. And physical layer, same as the physical layer in OSI model. And this deals with the actual network connection type of cable, the technology that is used to connect the network card to the actual network. Now when it comes to network, every computer needs to have a network card. Now then what is that is unique about that, so that every computer can participate in the network uniquely, this is more like a every person in United States has a unique SSN number, and that number represents that person. Similarly, every network card has something called a MAC address, or a physical address. That is the address that comes with the network card. You'll not be able to assign it. I mean, assigning MAC addresses or physical addresses, that is out of scope, beyond the scope of this particular video. But for now, I would request you to think in terms of the fact that every network card comes with a MAC address or a physical address that is burnt into the chip by the manufacturer. That MAC address is used for communicating between the systems at the physical layer. Okay, now that's an example of a MAC address. This is how it looks, and you can use IP config/all on your Windows machine to display the IP address properties of your computer, and it will also display your network card's MAC address. So that is, basic introduction into a TCP/IP protocol stack. And we'll wind this video with one more concept called port. So as as in any language, say English, you need to have some basic grammar skills to communicate, and without that, the sentences doesn't look right. The same way with the TCP/IP protocol stack, which is a communication protocol. Here, a blue computer trying to communicate with a green computer on the right hand side. So what do they need on the network so that they can communicate? Both the computers needs to have IP addresses, and they have to be unique. Both the computers need what? Network cards. And what does a network card have? Network cards have the MAC addresses. And in addition to that, for these systems to communicate, they need port numbers. Sorry, it should be two. So these port numbers, in other words, they could be same as well. Their port number here, let's say 21, it could be 21 here as well. But the port number here, there's a little difference. IP address is assigned by the systems administrator. MAC address is assigned by the network card manufacturer, and it is burnt into the network card. Port number is handled by the TCP/IP protocol stack. So for both the systems to communicate, you need IP address on both the sides. They have to be unique. They need what? MAC address on both the sides. Both the network cards should have the unique IP addresses. And of course, you need port number or some port on both the sides for them to communicate. And port number is what? Assigned by the protocol, TCP/IP protocol stack. Now, next thing. Standard ports. Standard ports are also known as well-known ports. 1,000 to 1 to 1024 are referred as well-known ports, and you're not supposed to use them for any purpose. These are some of the well-known ports. FTP uses port 21. Secure Shell uses port 22. Telnet program uses port 23. All your web browsing with HTTP uses port 80. And when you use your HTTPS, which is secure web browsing, uses port 443. These are the default ports, meaning if you don't specify, it will use the default ports. By that what I mean is, let's say in your browser, if you do www.google.com, what this means is you're saying use port 80 for communication, and it uses port 80. And when you log into your online banking systems, even if you try to use port 80, it will automatically direct it to HTTPS www.bankofamerica.com, and that HTTPS means it is using port 443. That is secure HTTP. So for two systems to communicate, just to recap, for two systems to communicate on the network, they need both the systems need IP addresses, and they have to be unique. Both the systems have to be on the same network. Both the systems should have network cards. Both network cards should have unique MAC addresses, and the MAC addresses are assigned by the manufacturer of the card, and they are burnt into the NIC cards or network cards. And they also need port numbers or ports, and the port number is assigned by the TCPIP protocol stack when the communication starts. Well, that kind of concludes this video. Thank you very much for watching.